So today we're talking about logarithmic functions. This is the parent function where the b stands for the base of this function. So this b stands for the base. And here I'm representing a whole bunch of transformations. What did you guys write on your paper for A? Yes. Y'all are missing a word. Vertical. So it's a vertical stretch if the absolute value of A is greater than 1, and it's a vertical compress if A is less than 1, the absolute value of A, okay? And the B is the base. How does the C transform your graph?
Horizontally.
Exactly, horizontally, left or right. And the D?
Vertical shift.
Yes, vertical shift, up or down. Nice, so those are the different transformations that we're going to be using today. Now, the most important one is the left and right movement, because that is going to affect your asymptote. You have a vertical asymptote whenever you have a log. You have a vertical asymptote. Please write this down. If your log function shifts to the left or to the right, that is going to affect the vertical asymptote, okay? Let's look at something we already know. 10 to the power of x. This is an exponential function. So we're going to review what we did the last unit. We would make a table, and we would always plug in these values. And when you plugged in a -2, you guys got 0.01. When you plugged in a -1, you got 0.1. 10 to the power of 0 is 1. 10 to the power of 1 is 10. And 10 to the power of 2 is 100. And we would graph this right here. -2.1, that's really small. -1.1, 0.1, and then 110. I'm going to say this is 10 right here. And it just goes off of the page. It grows so fast. So that was our exponential graph. Today, we're not going to graph exponentials. We're going to graph the inverse of an exponential. The inverse of an exponential function is a log function, okay? So this exponential has a base of 10. The inverse, the key word is inverse, also has base 10. So your log here, it's not written, it has a base 10. Remember, that's called the common log. Okay, so we have the common log. These are inverses of each other. Remember, when something is an inverse, you can switch the x and the y. So that's what I'm going to do. The table for a log will be 0.01, 0.1, 1, 10, 100. We switch the x's and y's, so now these are my new x values. My y values are -2, -1, 0, 1, and 2. So this was the table for 10 to the power of x. This is the table for log. And I'm going to graph it. At 0.01, I'm at -2. 1, 0. And then I'm going to say this is 10, 1. All right, so that is my log graph. All I did was take the exponential function that I already know how to find and then swap the x's and y's. And you have the log, okay? Okay, so let's try another example. We have log base 2. What is the exponential function that's the inverse of this?
2 to the power of x.
Yep, 2 to the power of x is the inverse, okay? We know how to graph this table, or we know how to find this table. We plug in those values. 2 to the -2 is 1/4 or 0.25. This is the table for 2 to the power of x. Now we're going to do the inverse. So for the log, these are my x values, and these are my y values. So we're not doing this one. This is our new table for the log. Now, we just plot the points, and you guys can answer these questions. I'm going to pause here and let you guys finish. We graphed our points. Here it is, and I drew my asymptote right here. The asymptote crosses the x-axis at 0, so it's x equals 0. For a log, your asymptote is always going to be x equals and then the number. Let's do the end behavior. As x goes to the right, as I go this way, as x goes to the right towards infinity, where is your graph going? Yep, it's going up. It's going up to infinity. Now, will your graph ever go to negative infinity?
No.
No, because there's a wall here. There's an asymptote. So we're not going to go to negative infinity. We're going to go to this asymptote. And your asymptote, we said, was at 0. So as x goes towards the asymptote, what's happening to your graph?
It's going to negative.
Yep, it's going down to negative infinity. So that is your end behavior. Your range is all real numbers. You can write it either way. It's pointing down to negative infinity. It's going to go down forever and then up forever. Your domain, it's from the asymptote 0 to the right, infinity. All the x's are to the right of 0. So you can write it either way. Remember, it has to be a parenthesis. If you put a bracket, that is wrong because you cannot equal an asymptote. The bracket means you can equal that number, okay? We're not including the 0. So you will not have a line underneath. That would be wrong, okay? You have the natural log. This is called the natural log. What is the base of a natural log? E. It's never going to be written, okay? Your base is E. That means, do you guys remember the table for E?
2.77.4.
Okay. All right, so that's our table. All you have to do is just swap the x and y, okay? So we're not doing this table. The natural log table is the same thing but reversed. So these are your x values, okay? Now, to move on so that you guys can do the more challenging problems, let me give you this scenario. A vertical stretch by 3. I moved it like this. So this is a vertical stretch by 3. Which direction did it move? Yep, left 1 and what else? Down 2. So guys, since it went left 1 for the x values, I'm going to subtract 1 since it went to the left. That's just for the x values. And then for the y values, you did a vertical stretch by 3, so you're going to multiply all of these by 3. And then, yes, you do it before you subtract. And then you'll subtract 2. Because order of operations, multiplication comes before subtracting, okay? And that will give you your new points, which you can plot here, and then you can answer those questions. You guys got it? All right, I'll let you guys try it. Ready, go. Okay, so now we're going to talk about finding the inverses algebraically. We just finished graphing the inverses. Now we're going to do it algebraically. So, in order to find the inverse of a function algebraically, we're going to interchange x and y variables, and then we're going to solve for y. So, for example, if I have this problem, the first step is to switch x and y. So this will be x equals 2y plus 1. Now, all you have to do is solve for y. So you should subtract 1. So that 1 minus 1, that's 0. They cancel out. And you're going to subtract 1 from this side. So we are left with x minus 1 on this side equals 2y. Next, we're going to divide both sides by 2. And that's your inverse. So the way you write inverse, you can do the little inverse symbol. Or if you had f of x in the beginning, say it was f of x equals 2x plus 1, then you would write the inverse symbol like this, f inverse. The little inverse symbols have negative 1 exponent. Okay, so that would be your inverse. All right, now, you could also write this as x divided by 2 minus 1 over 2. These are the same things, okay? You can split them up. All right, so that's how you find the inverse algebraically. Now, let's confirm whether we are right or not. Okay? Let's make sure that this is indeed the inverse of this. The way we're going to confirm it is by doing a composition. Okay? We're going to do a composition. And a composition is just when you plug a function inside of another function. If I plug this inside of here and get x, and if I plug this inside of here and get x, then they're inverses. Okay? So let's try it. So I'm going to prove that they are inverses. So I have my original function 2x plus 1. That's the original function. And we said that the inverse said that this was the inverse. So I have my original and my inverse. So to check it to see if they're inverses or not, let's plug this in. So I have x minus 1 over 2. Now, let's see if we simplify down to x. Okay, now hopefully you can see that these 2's cancel out. But if you don't see that, I'll show you algebraically. So this is 2x minus 2 divided by 2. You can split this up. And this is the complicated way, guys. I do not expect you to do this. Those cancel. You're left with x. What's 2 over 2? 1. What's negative 1 plus 1?
0.
So it's just x. That was our goal, to get x. Now, please, I don't expect you to have to distribute this. I want you guys to see that they just cancel out. Those cancel, you're left with x minus 1 plus 1, you get x. All right, now we're going to do it the other way around. This is my inverse. I'm going to plug the original function into the inverse. So instead of this x, I'm going to put parentheses right there. Okay, this is my inverse problem. Let's plug that original function inside. Okay, let's see if this simplifies down to x. I really don't need these parentheses anymore. 1 minus 1 is 0, so this is gone. We're left with 2x over 2. And those cancel. You're left with x. So guys, since we were left with x both times, that means these are indeed inverses of each other. Okay? We verified it using compositions. All right, let's move on. Now let's graph these two problems. Let's graph it. The original one, your y-intercept is at 1, and your slope is 2, so up 2 over 1. Okay, that's f of x. Your inverse, you can write this as x over 2 minus 1 over 2. So this one is your y-intercept. This one is your slope. And you can think of this as 1 over 2. So your y-intercept is at negative 1/2. So that's between 0 and negative 1, right there. And your slope is 1 over 2. So go up 1 over 2. Up 1 over 2. All right, that's your inverse. Do you guys remember what line it reflects across?
X.
Yep, y equals x. All inverses reflect across this diagonal line, which is y equals x. This one is your log function. This one was that exponential function. This is the diagonal line, y equals x. So what is the line of symmetry between the graphs? It's always y equals x if they're inverses. What is the inverse of 5 to the power of x?
Log 5.
Exactly, log with the base 5. This is the inverse. And they said let g of x represent the inverse. So I'll call this g of x. What's the inverse of a log with base 4?
4 to the power of x.
Exactly. This is the exponential. This is the inverse. Now guys, we need to rewrite this Because whenever you have base e, that's called the natural log. So the proper way to write this question would be f of x equals natural log of x. You won't really see that. Log with the base e, you write it like this, the natural log. Okay, so guys, what's the inverse of this?
E to the power of x.
Exactly. Okay, so this is the original function, 5 to the x. But instead of an x, I'm going to plug in that inverse, log with the base 5. And those will cancel out. It leaves you with just x. Here, our function is log base 4 of x, but instead of x, I'll plug in the inverse, 4 to the x. Those cancel. You're left with x. Yes.
Why does the log also cancel?
Because these are inverses of each other. Also, if you think about it, remember whenever you have this, I can do the power property and bring this to the front. What 4 to the power of what will give you 4? 1, so it's just x. So those just cancel out. Very good question. So I have e to the power of x, but I'll just plug in natural log, and those cancel out. You're left with x. Now let's do it the other way. So let's say I have log with the base 5. I'm going to plug in 5 to the x. Those cancel. Say I have 4 to the power of x. I'll plug in the log. Those cancel. Inverses always cancel out. You're left with x. And then our last one. Let's do ln, natural log. We're going to plug in e to the x. Those cancel. You're left with x. So guys, this is the big idea. Whenever you have your base raised to log with the same base, when these numbers match, it cancels out. You're left with x. Okay? Same thing here. Whenever you have log with a base and this number matches, it cancels out. It's just x. These are the two important things that you must know. Knowing these two rules, you can now answer questions A through F. Go ahead and try it. It should take you about 15 seconds. They all canceled out and left you with x.